And this is the 10-1 alpha lesson. I'm trying to get better at this confidence board, so don't mock me if it doesn't take very well. Oh, okay, so here are the bullet points we're trying to do. Ready? Center, shape, spread of this, the difference of two sample proportions. The difference between the two. Conditions, confidence interval, test statistic, the z-score and the p-value, and perform a test. That slide has to begin to make sense to you. The ones they're talking about is like, oh, it's just background. You don't understand what those things are referring to. So here's an example. You have school one, where 70% of the children did their homework. You have school two, where 50% of the children did their homework. And you want to build this confidence interval for the difference of the two proportions. So what would be the center of it? 20% or negative 20%. Doesn't matter. You can put negative 20%. You can do school two, take away school one, and the whole graph just got symmetrically reflected. You're going to get the same answer. So there's a sample of 100 students from school one and 200 students from school two. All right, they're the sample sizes. What are we going to do with this? We're going to do the conditions. So we have a simple random sample, right? 70% did their homework out of a sample size of 100. 70 is greater than 10. Didn't do their homework. 30% times 100 is greater than 10. The step would be success, homework, failure, no homework, divided by the sample size. The step is about 4.5%. And we're sampling that replacement, but it says, we expect there's more than 1,000 kids in the school. Then we go to the other one. 200 times 5/10 is greater than 10. And the step would be at 3.5%. And we're saying that we're assuming there's more than 2,000 kids in school two, or we wouldn't have taken that big a sample. Now, this is a simulation. Ready? The simulation was done with computer software, and what? The center's at 20%. Because that's school one, take away school two. And if you look at this thing, what's the likelihood that more kids in school two are doing their homework? Well, that would be everything at 0 and to the left, more kids for school two. That doesn't even make it on there. There's no dots that came up to there. So what about this one? Well, in that case, in that particular simulation, 72% did it in school one, 47 in school two. That 25% is one of the dots. Nothing particularly important about that particular dot. There's the center. Now, here is the step for the difference of two proportions. Ready? This is the variance for school one. Before you take the square root, that's the variance for school two. You add these variances and you take the square root of that. Which means what? That it's about 6%. So we would say that 20% more kids do their homework in school one, but that typically varies by 6% one way or the other. Somewhere between 14% and 26% more kids do their homework in school one. So if you meet the conditions, you expect the sampling distribution to be approximately normal. So what have we got here? We've got the mean, mu, the parameter mean of the difference of proportions. We've got sigma, the parameter step of the difference of proportions. Another example, we got goldfish. But I want gold with different colors. So bag one has 25% red cracker. Bag one is 25% red. Bag two is 35% red cracker. We're going to do the difference. One take away two. And what do they do? Your teacher takes an SRS of 50 goldfish for bag one and 40 for bag two. That's not a very COVID-safe activity. Sweaty hands, down the goldfish, and people are going to be eating them. So nothing to do with COVID, it's just gross. Okay? So, what do? We say, well, the sample size times probability of success has to be greater than 10, and it is. So all those numbers, 50 times 25% is bigger than 10, so 50 times 75% has to be bigger than 10. 40 times 35% is bigger than 10, so 40 times 65% has to be bigger than 10. You can do this in math. You can only take the smaller number if you say, therefore, the other one has to be bigger. So they understand you know what you're doing. The difference of proportions. If we do bag one, take away bag two, the center's negative 10%. The number doesn't have to be positive. We can do bag two, take away bag one, but it's either, it doesn't matter whether it's negative 10 or 10, because if we're switched, you're just rotating the picture. Here's the step. See, the important thing is the step, which again, we did this before and we're coming back to it. So this is bag one, success, failure divided by sample size. It's the variance for bag one. That's the variance for bag two. You add the variances and take the square root. So it's essentially 10%, one step. That's one step. If we wanted a 95% confidence interval, we would want 1.96 steps either way. So, conditions. There is no excuse for you omitting conditions on the AP test on the one, maybe two inference questions you're going to get, because these conditions are all over these PowerPoints. Right? And in the chapter 10 folder on Canvas, I have this template which is filled in for you. So chapter 8 and chapter 9 have a blank template in there. Inference template. Chapter 10's got one where it's filled in. So what are the conditions? SRS, if it's an observation, random assignment of treatment, if it's an experiment. If it's proportions, then you have to multiply n times p hat, n times 1 take away p hat, that's going to be greater than or equal to 10. If it's means, the sample size has to be at least 30. And you don't want the sample being more than 10% of the population. And if you do that, you even if you get the rest of the problem wrong, you earn the point for the conditions. So how about this? Brand names, they important to you? Well, they asked 2,300 US adults, 26% said yes. They asked 1,058 Germans, 22 said yes, 22%, not 22, 22%. So I have SRS. Those are less than 10% of the population. They're proportions. All of those calculations are greater than 10. So here's where we are. You have the test statistic. Add or subtract the critical value. So the test statistic, add or subtract 1.96, 1.645 times the step. Test statistic in this case is the difference of proportions. Now, watch what happens. That's sigma. The Greek letter is its sigma of the difference of the sample proportions. But if it's sigma, it uses values that aren't known. The true proportion. So if we put p hat in there, that's what we do know, then instead of sigma, we say it's the standard error. Because we're admitting we don't know the true proportion. It's just like when we say, I fail to reject a null, you're covering your backside. If you say standard error, you're covering your backside and said, I don't know the true sigma. How about if you had an experiment? So you get this experiment. They're saying this. You got back pain, and you've got people in this, you got these subjects, and they're all getting naproxen, whatever that is. Doesn't sound healthy. They're getting naproxen, and some of them are getting Valium with it, and some are getting naproxen with a placebo. And you want to compare, you want to do a 99% confidence interval. Okay, tell me right now, what is the test statistic for a 99% confidence interval? What's the critical value? Oh. What do you have to do? Inverse norm 0.005. Because if 99% is in there, 1% is outside.
It's 576.
That's you're close enough. So 1% is outside and the graph's symmetric, you would have 0.5% to the left and 0.5% to the right. So what happened? 39 of 57 subjects who took the treatment reported less lower back pain. 43 of the 55 in the placebo group, less back pain. So what did we get? Well, actually, if you look at this, you can tell that the placebo worked out fine. So here is your confidence interval. You're 99% confident that the difference in proportions is in there. Now think about this. What number are we looking for in the confidence interval? Looking for 0. Because if 0's in there, there was no difference. Yes? And if 0's in there, you F2R. But if the confidence interval goes from negative to negative, or positive to positive, then 0 is not in the confidence interval. And if 0 is not in there, there's a difference. You're 99% confident, there's a difference in proportions. But in this case, 0 is in there. So 0 means there's no difference. And if it's in the confidence interval, we would fail to reject the null. Okay? Well, I don't think you would do that. I hope not. So, here is the summary, which I'm saying. Center, shape, and spread. It's approximately normal if you meet these conditions. The variability is the sum of the variances. Take the square root of that. And that takes you this algorithm, which is centered about the statistic, P hat. You got to look for that thing. When you see a hat there, that means that is a statistic. Okay, and I apologize because sometimes the hat shows up on the PDF, sometimes it doesn't, and I went back and tried to fix that and couldn't get it to take. So I will call, if you're not sure, ask, and I will tell you whether it's supposed to have a hat. So we're going to pause the video and you're going to go do one set of problems. 1 and 3. Number 1, the conditions are met. All these proportions are greater than 10. 50 times 30% success, so therefore 50 times 70% has to be bigger than 10. 100 times 15%, so the other one has to be bigger. So the difference is 15%. That's what's in the center. Okay? 30%, take away 15% is 15%. And what's the step? The step is this, about 7.4%. Where are we getting that? First variance plus the second variance, square root of that. So I counted out 7.4% to the right, 7.4% to the left. Now the question in B says, what's the probability that the adult candy has more red? Well, the adult candy having more red would be fine 0 over here in this picture and everything to the left. Because this 15% represents the child candy has more reds. So we said, all right, let's go normal CDF. Everything from the left to 0. That's all the negatives. And the negatives are the adult candy has more reds till you get to 0, where the center is 15%, and that's the step. And it's a little more than 2%. If the company's claim is true, the probability of getting more red candy in the adult mix is a little more than 2%. And this picture and then that calculation should make sense to you. Okay? And you have to relate this to what we did in the fall. So, if you're at home